those of you just entering, yeah, just as a reminder, today is pretty much I'm going over problems from the logarithmic function section in the homework. The homework's due tonight. And so all that fun stuff. So yeah, hopefully you've all received my emails, in particular, yeah, signing up for the final exam, and then I switched some of the due dates around because of the hurricane. So hopefully you've all read those emails. So yeah, besides for that, I think everything's pretty much quantified very well, stated pretty explicitly on those emails. So I said I'm going to just do problems from the logarithmic function section that I haven't talked about that I didn't talk about in the video lecture. I was going to start with 20 and 21 because I know people have struggled with these in the past, and I think a few people have already this semester. So let's just go ahead and figure 20 and 21 out. So start off here. So we're trying to graph these two functions right here, 9x and log base 9 of x. And so let's kind of foreshadow what the graph is even telling us to do. So one of these functions is an exponential function, and the other one is a logarithmic function. So we could go ahead and start off with the exponential function, which if you just hover your mouse over, it'll tell you the exponential tool. So we'll go ahead and click on that. And as soon as we click anywhere on the graph, it's going to bring up this box. So there's no point in trying to figure out too specific of information in the beginning. So the exponential function we're trying to graph it's 9 raised to the x. Now that seems like a pretty basic function to me. There's no stretch or compression because that would imply that if there were a vertical stretch or compression, that would be a number multiplied to the 9 raised to the x, so the exponential function, like the 3 is in that quick example I just wrote down. But we don't have that situation. So that's a 1, and horizontal stretch or compression, that always stays as a 1. There's no shifting at all because there's no addition. There's no reflections because there's no minus signs. So the only thing we change is the base. The base, instead of it being e, it's 9. 9 is the base. Notice how the graph changes ever so slightly. So here's e, here's 9. It changes ever so slightly, but that's it for the exponential part. So we're already done with the exponential part. And there's also a logarithmic part, which is the log base 9 of x. And I like to use parentheses. But so now we go and graph the logarithmic function, which if you hover your mouse over all of these, you'll see that this arc here is the logarithm tool. And if you plot the first point anywhere, just touch the graph anywhere, another box comes up. And so again, we need to figure out what's the stretch, the shifting, and the base. Well, just like before, there's no vertical stretch or compression because we're not multiplying the logarithm by a number. There's no shifting because there's no addition happening at all or subtraction. There's no reflections because there's no negative signs. Really, the only thing that changes, and yes, logarithms have a base. The base is that subscript, as it's called. It's the tiny number here, as we'll start to learn over the next few, really the next few weeks. But the base of the logarithm is 9. Again, the graph changes ever so slightly. And really, that's it. That's it for this problem. So it's one of those problems that seems a little bit confusing at first. I've seen students struggle with it previous semesters, but really that's all there is to this problem right here. So hopefully that makes sense, everybody. And additionally, yep. And let's see if 21 is the same. If 21 is the same, yeah, 21 is pretty much the exact same problem as well. See, I could knock this one out pretty quickly. Yeah, you go and graph the exponential part. The only thing you change is that the base is 1/3. Oops, whatever. So, I notice it's interesting though. It's a food for thought though. When I typed in, so the base before, I think it's an E. I notice it has this shape, but when I put in 1/3, flips around the y-axis. It reflects about the y-axis, and that's because 1/3 is a reciprocal of 3. And when you have a reciprocal, you have a negative exponent. What happens when you have a negative exponent? You have a negative on the x, which means you flip about the y-axis. So you don't really need to know that because the graph does it for you. But if you want to think about this conceptually, as in, why did this graph just flip randomly? It's because the 1/3 is just 3 reciprocated. When you take the reciprocal, that's the same thing as having a -1 exponent. And so having a -1 exponent means reflecting about the y-axis. You're making the x negative. So just if anyone cared to know that reasoning, that's why. And the same with the logarithm like we did before. We changed the base to 1/3 and notice same sort of interesting shift or reflection rather in behavior occurs. So if you were interested in that, that's why that's happening. But yeah, that's 20 and 21. And so did anyone in here have any specific questions? I mean, I don't mind just going over random questions, but if anyone had a specific question from the homework, I'm happy to answer it. Shannon, you don't? Well, let's
Could you possibly, I'm sorry to interrupt you. Could you possibly explain the last one? I think it's 35.
okay, yeah, sure.
Thank you. I'm sorry to interrupt.
Oh, no problem. The last one. So I'm hoping it's this weird thing with the concentration of hydrogen. So I'm gonna go off of this one. Okay. So okay, so the pH of a chemical solution, I don't know. It sounds pretty boring to me, but they do give an equation, so that gives us something to start with. They tell us that there's this logarithmic formula here, negative log base 10 of H plus. And this is something about concentration of hydrogen ions. So if you want to clean this up, if you don't like the notation that much, you can always rewrite it as, and I'm just going to rewrite it here. If you want it to be less technical, you could just replace the pH and the H with f of x and x. Or if not, that's perfectly fine. But for the first part, it's saying when is the H plus part 0.01. So in other words, it's wanting you to plug in 0.01 for x and find y. And so this one, it's pretty much, can you put this in your calculator? But in my video, hopefully by this part, I explained this in the video already. So the question is, how do you put how do you put this in the calculator? And the way you put this in your calculator, because the calculator will not take that base 10, the base 10 there. Or at least these calculators do not. You have to have these calculators for the final. So the way you rewrite it, hopefully you remember, hopefully I did talk about it by this point. It'd be log of the number straight to the right divided by log of the base. And notice the negative sign is still in front because it was in front before. So that just carries over. And then you can put all of this directly in your calculator. And what you should get is like -2, -3, something like that. Maybe even -1, I don't know. We'll find out. Negative log of 0.01 divided by log of 10. And I get 2. Oh yeah, you should get 2, right. Okay. Well, let's make sure we get 2. So really I believe the next 2 parts are the same thing, except now it's equal to 0.001. So they're just adding an extra 0. So I'll kind of breeze through this a little bit quickly. This one should probably be 3, is it? Let's find out. Yeah, it's 3. So it's the same exact process, just a slightly different number. And they add one more 0. I just happen to know it's going to be 4. So by doing the same exact work. So I'm just going to breeze through that one. And so part D wants us to determine what happens to the pH balance as the hydrogen ion concentration decreases. So that sounds a little technical. So if you want to go back to using Y's and X's, pH was Y. What happens to Y as X decreases? Because remember, we used X to represent that wonky thing and Y represents the pH. So as the X values decrease, so as we went from 0.01, 0.001, 0.0001, the pH increases because we went from 2 to 3 to 4. So that's what it's asking about. And then probably the more intricate part is what I've just stumbled across now. So now it's giving us the pH value, which is telling us that Y is equal to 3.5, and they want us to solve for X. So what we're doing now, we're setting the whole logarithmic function equal to 3.5. And I'm going to say of X, just using the notation we had before. So now we need to figure out how to get X by itself. So I'm trying to remember how I explained it in my video. If anything, we can bring the negative sign to the other side by multiplying both sides by -1. So notice the negative sign just went to the other one. Because if anything, definitively what you want is the logarithm to be 100% by itself. You want the logarithm to be by itself completely. And here's the logarithm by itself. The negative sign in the very front did not have the logarithm by itself. And so this is where I talked about that perhaps, or hopefully you remember the windmill method. And it depends on however you wrote your logarithm. this windmill method may be different depending on what side of the equal sign your logarithm is on, but it has to go in this order. It has to go in this order, which means that 10 raised to the negative 3.5 is equal to x. And then it tells us to round to 6 decimal places. So let's see what this looks like in the calculator. 10 raised to the negative 3.5. I have 0.000316. Is that right? Cool. And when I put this in the calculator, let me make sure. Okay. What I was going to say was it might be good to keep your exponent in parentheses when you put it in the calculator. I just tested it. It doesn't change anything, but I guess it's just good to keep in mind. And then the next part says, well, I changed my mind. I don't want 3.5 as the y anymore. What about 7.1? So we can do the same exact problem, but with 7.1. And it works out the same exact way. So in fact, I'm just going to write down 10 raised to the negative 7.1 is equal to x. Because it's the same problem, just replacing 3.5 with 7.1. You do the same exact steps like we did before. You throw this in the calculator. And then notice it doesn't want us to type in the answer. It wants us to select the correct answer in scientific notation. So the way scientific notation works, well, generally you want a one number before the decimal. So it'd have to be either the second choice or the fourth choice. And so I'm just going to count all the zeros, or count how many spaces it is until I get the decimal behind the 7. 1, 2, 3, 4, 5, 6, 7, 8. 8. There's also a way in the calculator you can convert to the scientific notation display, but it would only be useful for this one problem. But if you can figure out how to put the calculator scientific, I know that's probably impossible to see. So, but there's a 10 raised to the negative 8 over here, if you could figure out how to put it in scientific form in the calculator. But yeah, other than that, you could just count the zeros or count the decimals until you hit wherever we were at here. So you get the decimal behind the first digit, how scientific notation works. And so, yeah, that completes number 38. Were there any other specific problems, or I guess if not, I'll just go through just the problems I haven't covered. Okay, and so I'm going to do this in tandem with my class notes. So let's see, I talked about logarithms and natural logarithms. So hopefully you were all familiar with those concepts by now, and definitely hope that you are, because you're going to be seeing logarithms for the rest of this class. The remainder of the material we talk about is logarithms for the whole remainder of the class. It's always about logarithms from here on out. So So just some of the for definition's sake, the domain of a logarithm. Oops, that's not it. It's not all real numbers. The domain of a logarithm is there's a vertical asymptote on the y-axis, which means that all the values continue to the right of that vertical asymptote. That's why the domain is from 0 to infinity. But you may notice in that same thought process that the range is all real numbers because it goes down and up without any barriers. So let's see, which domain problems did I talk about? Let's find out. Okay, so I did a domain problem very similar to this one. For example, I talked about number 4. Probably a lot of these you all figured out. I suppose I'll just do 6 just as a warm-up. You might know how to do it, but so with a problem like this, it's just asking for you to rewrite as a logarithmic statement. And as you've probably figured out through the section, if you've been doing the problems already, that sometimes it's helpful to rewrite things as logarithms because doing that may help getting the x by itself, or sometimes it's helpful to write from a logarithmic expression to an exponential one. Just depending on where the variable is at. And so the rule, as I stated in my notes, so whatever the base of the exponent is the base of the logarithm. So that's a little bit more helpful. So if anything, the base of the exponent is always the base of the logarithm. And then you're taking the logarithm of what everything's equal to, and that would be equal to the exponent itself. So these two mean the same exact thing. In fact, the bottommost statement is the logarithmic statement, the equivalent logarithmic statement. So that is a conversion that you would need to know for the test. Converting from exponents to logarithms or logarithms to exponents. Again, that conversion is here. So just wanted to say that as a warm-up. And I talked about the E in the video. But yeah, E comes up E is very much related to the logarithm. In fact, it's such a common occurrence that you may notice that log E is exactly ln. And we use ln quite a bit, which is why it's given its own name in this section, and just in general in mathematics, because E comes up quite a bit. And I explained E more in my lecture video. I'm just going to skip that. And then I'm pretty sure I did a few of these. So let's see. So I did this one in the notes, so skip that. Yeah, and I went on to talk about some of the exact values. It does say without using a calculator. You can ignore that. I think I said that in the video, but if not, you can ignore this. So pretty much for example 3, I'm pretty sure I hope what I did was explain how to type this in the calculator. And then I'm telling you, you can use the calculator. So you are allowed to use the calculator. And so I did this one in the notes already, so I'll skip it. Did that one, did all of these. And then additionally, as far as the domain of the logarithms go, the domain of any logarithm. So we have talked about quite a few domain criteria before. The set the denominator not equal to 0, or if there's a square root, you get rid of the square root and set everything underneath greater than or equal to 0. In this problem, or for the in particular, the domain of logarithms, I explained to take whatever is within the logarithm, whether it's a logarithm or a natural logarithm, it's the same approach, and set that strictly greater than 0. Not greater than or equal to, just strictly greater than. The reason why you don't consider the equal to part is because there's the asymptote on 0. So that's why you're excluding, you're excluding the asymptote, which is why it's strictly greater than 0. But from there, it's really easy to solve, which should be the case for most of the problems, I would imagine. And then you're just required to convert or rewrite from an inequality to interval notation. So this would be, of course, 2 to positive infinity. So I explained that in the video. If that was all pretty straightforward, then yeah, that should help you with the next few. I did problem 19, and I just talked about 20 and 21 at the beginning of class, so I'm going to skip over those. I think it's worth doing another one of these. Might do 22. Let me come back to it. 23 looks similar to example 5. So let me see what else is. Okay, I'll do 22, just to explain my approach on this. So I'll go ahead and do 22 from the notes. And so we have seen problems like these before, where they give you a graph and you have to match it to the corresponding function. Now, they do tell us that this is a logarithmic function. They tell us this is a logarithmic function, which means we know what the parent shape looks like. The parent shape, or what's the original shape look like, in other words. And we know that it looks like this. And you can look this up in your notes. I'm just rewriting what the logarithmic function looks like in its most basic form. So knowing what the parent function looks like, what the original logarithm, this helps us see how we go from the original function to, or the original graph to this new graph here. And you might notice with the new graph, there's a reflection here. If anything, there's a reflection. So there's definitely a reflection. So what kind of reflection is that? It's a reflection, it looks like about the x-axis. So the whole function should be negative. So remember, that's what it means. For the x-axis to be reflected, the whole function needs to have a negative in front of it, which instantly means we can cancel out a good majority of these, actually. A is out because there's no negative in front. C is okay. E is out. G is out, B is okay, D is okay, F is out, H is out. And D is okay because there's a negative in front of the logarithm, and that's the important part. So B, C, and D. And from here, we just need to figure out, okay, now which one of these resembles the graph? Now, one thing you can try and do, you can knock this out really quickly by using a test point. So this seems to be a definitive point on the graph. So what that point tells you is whatever the correct function is, you better be able to plug in 1 for x and get 0 for y. And really, there's only one. Really, it looks like there's only one that does that. I mean, there's other criteria you can use as well. This one's probably the most definitive. So for example, if we tried answer choice B, which says y is equal to negative log base 4 of negative x. Negative log base 4 of, well, now negative 1, because we're trying the test point out. Well, how we evaluate this is negative log of negative 1 over log of 4. And if you try putting this in your calculator, you're going to get some kind of error. It's going to say a domain error. And so that tells you, okay, well, B is definitely not right because you can't even plug in 1 and get an answer. So B is out because we can't even get an answer from it. So B is gone. What about C? So this is negative log base 4, and instead of x, I'm going to put 1. So that's negative log of 1 divided by log of 4. Let's see what this is going to spit out an answer. Let's see what kind of answer we receive. And we get 0. So that's pretty convenient. So that matches the y value here. So it doesn't mean it's right necessarily. It just means that we can't eliminate it now. But as we find out for answer choice D, one minus log base 4 of 1, 1 minus log of 1 divided by log of 4. And you end up getting 1. You will end up getting 1 here, which is not the y value that we needed. So it has to be C. Another way you could have eliminated answer choice B is because B had too many negatives. It had too many reflections going on. It said there was a reflection about the x-axis from the negative sign in front, and a reflection about the y-axis as well, because there was a negative in front of the x. D would have been a little bit more complicated, because technically reflecting and then shifting up by 1 may not be as easy to determine in this problem. But the answer choice is C. And that's my thought process on how. So knowing the parent function helps you narrow down considerably. And then a test point will pretty much wrap it up from there. Okay. So I suppose let's keep going. And I did one, 23 looks very similar to the one I did. Example 6 is pretty much problem 24. So I'll skip that one. So natural log of x plus 6, natural log of x plus 4. So I'll skip it. Might do 25. me check the other ones. Okay, I'll do 25. Okay, so 25 here. They first want us to determine the domain. Well, the domain is whatever's in the natural log or whatever's in the logarithm, we set that greater than 0. The logarithm's right here. The part within the logarithm is x, and so we set that greater than 0. Well, that was pretty easy. It just solved itself, really. But we have to put this in interval notation. Now it wants us to choose the correct graph of the original function. And really, it seems as though the changes here are shifts. This one, choice A seems to be shifted down some amount, which ends up being 6. B seems to be up 6, to the left 6, and to the right 6. So really it's asking, in other words, it's wanting us to determine what that negative 6 is doing. And remember, when you're adding or subtracting the function as a whole, that tells you up or down. And it tells you verbatim that it's down 6 because it's -6 or -6. So it makes sense that we pick the graph that's actually going down 6. And then now that we have the graph, we can figure out the range. But the range of any logarithmic function is all real numbers. It goes down forever and it goes up forever. And that's always true for logarithmic functions. The range is always all real numbers. Okay, so that's the first 3. We still have, looks like, a few more parts left. They're also asking us for the equation of the vertical asymptote. Well, we technically found the vertical asymptote in the domain. Really, the vertical asymptote is going to be x is equal to that number. Because the barrier number, or the number in the domain that we're using, that's represented by the barrier. And we are excluding the barrier because we're using parentheses, but that barrier is the vertical asymptote. If that doesn't make any sense, then all you have to do is pull up the graph and see for yourself that the vertical asymptote would happen wherever the graph stops going in one direction continuously, one direction left or right continuously. That's at 0. So that's 2 ways of determining it. Now it wants us to find the inverse. Hopefully you remember from the inverse section, this means switch x and y and solve for y. So in the original equation, the original function, we switch x and y, and now we have to get y by itself. So we can add 6 on both sides to get natural log of y by itself. And now we need to get rid of the natural log. From my video, I explained that the way to do this is you have to apply e on both sides, but in this weird way where you apply the exponent, or you apply a base of e and you make everything that was there before exponents. So notice x plus 6 becomes an exponent. Natural log of y becomes an exponent. And the only reason why we do that So E and ln will cancel. And I'm just going to swap them just for aesthetic sake. And then we get e raised to the x plus 6. And then it wants us to find the domain and range of the inverse. That's weird because they don't give us a graph. But we already know the domain of the inverse. So hopefully you remember from a few sections back. The domain of the inverse is the range of the original function. We found the range of the original function. It was all real numbers. So guess what the domain is of the inverse is? All real numbers. Oops, a little slash in there. Okay. So the range of the original function is the domain of the inverse function. That's why I said we already found the answer. The range that we found up top here is the domain of the inverse. That's one of the good things about finding an inverse or knowing information about the original function. And so the range of the inverse is the domain of the original. The domain of the original was 0 to infinity. That means this one is 0 to infinity. It's the same exact value. Finally, we want to figure out so let's see, I'll rewrite the inverse function. We need to figure out the correct graph of e raised to the x plus 6. And now you notice that there's graphs going up, down, left, and right, which means what is the 6 doing now? Well, that 6 is adding the x directly. Adding or subtracting the x directly means left or right. And in particular, we have to go the opposite direction. So plus 6 means left 6. So we need to pick the one that's going to the left 6. And it looks like answer choice D does that. So that's problem 25 from the homework. So it goes on to asking you to solve logarithmic equations. So I did one. Actually, I'll do this one just to kind of motivate it. You might already know this one, but this one shouldn't take long. So this would be the most basic introduction to that conversion method that I talked about, the windmill method. Because when we are stuck at a logarithmic equation and we need to, if we're stuck at it, not knowing what to do, then it's normally a good time to rewrite as an exponential equation. And the way you rewrite a logarithmic function as an exponential, I've seen students over the years do this windmill method, which characterizes the order in which everything is placed in the new exponential form. I mean, if anything, the base of the logarithm, 8, is the base of the exponent. Just the exponent is going to be 2. And of course, 8 squared is just 64. And so for the problems I talked about in the lecture, I no doubt went through that same process. Okay, so I talked about number 28 in part 1, it looks like. So I talked about 29. I talked about this one as well. This one has just one thing that I just want to point out. So you may notice that on the left-hand side, so the logarithm on the left-hand side, there's no variables over there. And this is going to come up, really this comes up a lot more in the next section, but I wanted to identify it now. So some people would take this problem and try to rewrite it like this, and then try to get a common base. And you get that x is, what, -1. So some people do it this way, but there's an easier way. And I'm going to show the easier way because this is going to be helpful in the next section, actually. So let's just start over. Well, because everything on the left-hand side is already just nothing but numbers, that means you can attempt to simplify it. This is the same thing as log of 4 divided by log of 2. And in the calculator, that's just 2. Well, let me make sure that's 2 before I start messing up. Yeah, it's 2. So really, this problem, without having to do any sort of revision to the problem, log base 2 of 4 is just 2. And we can make that simplification because that logarithm had no variables on it. Again, you'll notice this in the next section as well. This happens a little bit more. And if you can make that identification that you have a logarithm that doesn't have any variables on it, well, try to see if it simplifies. Because notice now, we just have a linear function. And you could solve that really easily. So I just wanted to give everyone a heads up about that situation. Okay. Let's keep going. So let's see. They start talking about E as well. And I'll just do this one just to motivate the idea of E. So normally, so the thing to keep in mind is that E and ln, the natural log, and don't ask me why it's natural log and then abbreviated, it's ln. I'm not too sure about that one, but yeah, whenever you see an E and you're trying to get rid of E, the number E, you want to apply an ln. Or similarly, if you're trying to get rid of ln, you want to apply E. So really what you're doing is you're applying ln on both sides. And by doing that, the ln and the E being right next to each other, they cancel out. So what you get is 3x is equal to ln of 5, and x is equal to ln of 5 divided by 3. And it's not ln of 5 divided by 3. It's ln of 5 is one number. ln of 5 is one number. It's one quantity. And they want an exact answer. So if you were wondering why, so if you're trying to type in this, that's going to be wrong. You have to type in ln of 5, and you're dividing ln of 5 by 3. So huge distinction. In fact, it's gonna, if you make that, if you have that misconception on the test, you'll lose some points, and that wouldn't be too helpful. And I'll talk about another one in the video for a little bit more practice. Go ahead and talk about this one as well. It just wants us to solve. And so really, my first step is going to be rewriting this as an exponential. The way I'm going to do that, remind myself how the exponential is formed from these numbers. It tells us that it's 5 raised to the 4th power is equal to x squared plus 9. You might have already noticed that this is going to be a quadratic equation. So we can subtract 625 on both sides because this is a quadratic. 9 minus 625. And because there's only one x variable, we don't have to use the quadratic formula. It's a pretty interesting looking problem. Yeah, 616 is definitely not a perfect square. Can we simplify it though? By 4? Okay, we can take out a 4. So 616, you can definitely take a 2 out of it. We're left with 308. And we're only doing this because they're making us put an exact answer. $154. And then 2 and 77. So we have a pair of 2s that can come outside. But the 2 and the 77, they do not have a pair, so they have to stay behind. So 2 times 77 is 154. Let's see if this works. These are some interesting numbers. Or okay. Interesting problem, but glad I did that one. So that problem was a little bit complicated because we don't really find ourselves in too many situations where we simplify radical expressions. But if you're struggling on number 34, you can use this as reference for when I post the video. Okay, let's see. We're getting close to the end. Let's see what else there is. And I talk about number 35 here in part 4 of example 8. So I'm going to skip that. I talk about number 36 in part 2 of example 9. So I'll skip that. And I talked about 38. So I guess I'll talk about 37 and it'll be everything I have. So we have some logarithmic expression here, and they want us to find the domain. So the domain, you take the logarithm part, and in particular what the logarithm's evaluating, which is the 2x minus 1, and you set that greater than 0. That's just the rule. Every time you set whatever you're taking the logarithm of greater than 0. 2x is greater than 1, x is greater than 1 over 2, 1/2 to infinity would be the corresponding interval notation. Part B, they just want us to plug 41 into the logarithm. So let's see, this is log base 3 of 41 times 2 is, 41 times 2 is 82, and that's 81 minus 3. And then what is that, 4 minus 3? This is log of 81 divided by log of 3 minus 3. Let's see, is this 1? Let's find out. Log of 81 divided by log of 3 minus 3 is 1. So it is 1. Cool. Okay, and then once a point on the graph, when we plugged in 41 for x, we got 1 for y. They also want us to determine what happens when y is 2. So let's go ahead and do that. So they want us to set the whole logarithm equal to 2. And so we can add 3 on both sides. And then once we have a logarithm isolated, we can go ahead and rewrite it as an exponential. So 3 raised to the 5th power is equal to 2x minus 1. 3 to the 5th power is 243. And then we get that x is 122. And the point on the graph is just 122, 2. So finally, they ask for the 0. And remember, the 0 just means the x-intercept. So they want us to find the x-intercept, in other words. So now we're setting the function equal to 0. I'll probably need more space than this. I'll figure that out at that moment. So we can add 3 on both sides. Pretty much the same thing we did before. And from here, now that we have the logarithm isolated, we can rewrite it. 3 raised to the 3rd power is equal to 2x minus 1. 3 raised to the 3rd is 27. And then x looks like 14. So I think up to there, that's every homework problem explained either from my lecture video or from this homework review session. So if you don't have any questions about anything, then that's really all I have for today. If you do, I'll stick around. But have a good day.